Hello everyone and welcome to this presentation. My name is Marco Franceschetti. I am a PhD student at the University of Klagenfurt in Austria, and today I am presenting you a recent work which has been conducted together with my supervisor, Professor Johann Eder, and the title of this work is Designing Decentralized Business Processes with Temporal Constraints. Now, to give you somehow a frame of this work, here we are addressing inter-organizational business processes, which are an increasingly adopted approach to realize business applications. In an inter-organizational business process, we have several partners who cooperate by composing their local processes in such a way that the business process is emerging from the interaction of these loosely coupled local processes. Typically, the interaction in this context is realized through the exchange of messages between the involved parties. Typically, the implementation of the local processes is kept private, and only interfaces or process views are made available for the other parties. So there is a sort of black box approach here, in which each of the parties is exposing only the minimum necessary information to the others, such that this enables the cooperation. And this also allows, on the other hand, to maintain the business secrecy unharmed. In addition to that, to guarantee an effective collaboration, there are contracts, in particular service level agreements, SLAs, which are stipulated between the business partners. These service level agreements are used to specify interfaces, protocols, and service qualities. Among these SLAs, we have the temporal service level agreements, and these define basically temporal properties which need to be fulfilled by one party and are expected to be fulfilled by the counterpart. Examples for temporal SLAs may be maximum response times or the validity periods for some data objects such as a one-time password, for example, which needs to be used within 5 minutes after it is received, then it expires. Or other restrictions on the time of occurrence of certain events. What we need to say about these restrictions is that typically they are expressed in terms of inequalities between the timestamps of events. Now, to give an example, let's consider the ground operations at an airport. Ground operations is basically an umbrella term for a large number of coordinated operations which are carried out by several companies from the time an airplane lands at an airport to the time it then leaves it again. Here we are considering for simplicity only 3 companies: a ramp services company, the airport company, and the logistics company. We have a number of activities here. We can see in the process of the ramp services company, reach plane and load plane, for example, which have specified a minimum and maximum duration, meaning that that activity will take some time between the minimum and maximum. And actually, we can consider them as contingent, which means that their actual duration cannot be controlled, but it will only be observed as it is performed at runtime, because typically these operations depend also on other factors which are not under control of the executor. So this is also somehow giving a sort of uncertainty in the whole process execution for what concerns the duration in this case. In addition to that, we have 2 temporal constraints, which are depicted here with these dotted arrows. First temporal constraint is the following. The logistics company can route the baggage not earlier than 5 minutes after the task for loading the conveyor belt has been completed. And another temporal constraint says that the airport company can deliver the baggage at most 16 minutes, so open the carousel at most 16 minutes after the conveyor belt has been loaded. And these constraints need to be fulfilled for a temporally correct execution of the process. Now, of course, here we have a number of collaborating parties, 3 companies, a number of tasks on which they may not have full control on the duration, and a number of temporal constraints which they together need to make sure they are fulfilled. So how can we actually model the interplay of these various local temporal requirements, and how can we guarantee that no time failure will occur? So in the following, we are going to show a solution to that problem. What we propose with this work is to extend process modeling notations with the use of temporal variables. What are temporal variables? Basically, they are data elements, part of the process data, which encode the timestamps of events. And these temporal variables can then be exchanged via messages between the local processes composing an inter-organizational process. They can be exchanged via messages as parameters, basically. Therefore, we can also call them temporal parameters, actually. And by imposing local constraints on them in the local processes, we can actually realize the temporal SLAs, which we have talked about in earlier slides. Therefore, we can constrain temporal variables by putting restrictions on them of basically 2 kinds. We can set range constraints, which impose a temporal variable, which allow a temporal variable to take only certain admissible values between a minimum and a specified maximum. We can also, of course, constrain them in relation to other time points or other temporal variables. So in the example that we see in this slide here, we can constrain a variable v to take a value within a range vmin vmax, as well as a variable w to take values only between wmin and wmax. And we also constrain them to be in a relation such that v can take a value which is no more or equal to w plus 10. Therefore, by using temporal variables and their exchange as temporal parameters between the local processes, we are able to express temporal constraints between local processes in a collaboration without the need to exhibit the process internals, because now we are encoding timestamps of event which are internal of a process into a data element, and we are exchanging that data element to other processes. Therefore, we are complying with the black box approach, which I have mentioned earlier. Now, I've told you about uncontrollable durations, temporal parameters, and so it's time to say when all these temporal aspects for a process make up for a temporally correct process. Now, what we consider here as the notion for temporal correctness of a process is dynamic controllability. Dynamic controllability is basically asking one question. And this question is it possible to find a schedule which meets all the temporal constraints in the process under all the foreseeable circumstances which may affect our process? And what are these foreseeable circumstances which cause uncertainty? These are the uncontrollable durations or contingent durations, which I mentioned earlier, and values of parameters, temporal parameters, which are assigned by some other local process on which there is no control. Now, we say that cross-organizational business process is dynamically controllable if all the composing local processes are dynamically controllable. Therefore, we will need to find such a dynamic schedule which meets all the temporal constraints under all the foreseeable circumstances for all the local processes. And in particular, we need to take care about these uncontrollable durations and the values which these temporal parameters may take. So we need to have some way to perform some temporal reasoning on our process models. What we propose here is to use some existing formalism and adopt techniques which have been designed and are established for this formalism. In particular, we are targeting temporal constraint networks and more in particular, simple temporal networks with uncertainty, or STNUs for short. We propose to map each local process taking part into an inter-organizational process into a STNU and employ STNU-based temporal reasoning techniques to derive temporal knowledge about the process model. Basically, STNU, I will be brief on that, is a graph-based formalism, which is composed of nodes and edges, where nodes represent time points and edges represent constraints between time points. We may have controllable constraints between time points and contingent constraints between time points, which are basically representing those durations which can only be observed to occur within a given range, but it cannot be controlled. One of the first applications we can benefit from the formalism of STNUs is the check for dynamic controllability. In fact, there is a number of algorithms and procedures which have been developed in time for checking the dynamic controllability of an STNU. Most of them are based on the propagation of constraints or propagation of these existing edges in a network. And we say that the process is dynamically controllable if its equivalent STNU is dynamically controllable. So now we can check whether a given process model is dynamically controllable by mapping all its composing local processes into STNUs, performing the dynamic controllability check for these STNUs, and in the case all of these are dynamically controllable, then the interorganizational process is dynamically controllable. Another application we can take advantage of from constraint propagation is for computing ranges for input temporal parameters when these are missing. We may want to compute actually the largest possible ranges we may accept in a local process for the input parameters, given the ranges that we know already for the output parameters which we can promise. Of course, these may be dependent on each other. Why the largest for the input parameters? Because we want to give as much freedom as possible for our collaborating parties in assigning values for the parameters which for them are output. So for example, in the image we have here, we may derive that for a local process, a certain variable v is allowed to take a value between 3 and 48 such that dynamic controllability of the local process is ensured. Dual to that, we can also employ these constraint propagation techniques for STNUs to compute ranges for the output temporal parameters when they are unknown, and they depend on the ranges for input parameters and other constraints on input parameters which are known. In this case, we aim at computing the smallest possible ranges of values because we are providing someone else a parameter, and the smallest is the range of values which we can promise, the more flexibility we would allow for the other party which is receiving the parameter. In addition to that, we can also compute missing ranges and other restrictions for temporal parameters when these are not known, again by applying constraint propagation techniques which would derive, for example, in the image we have here, the missing unknown restriction that a given temporal parameter v has to be less than or equal to the value of another temporal parameter w plus 10. Finally, and this is very important and relevant in the case of cross-organizational business processes, is the negotiation of parameter restrictions. What do we mean by that? Basically, a parameter is used by more than one process, and each local process may derive different restrictions for that parameter. And if we have even more than two processes who are using that parameter, we may have a larger number of restrictions for that parameter. And of course, there is a need to find the trade-offs between all these restrictions which come from different local processes, and we need to find common restrictions such that we are sure that the values which we are allowing for a certain parameter will ensure the dynamic controllability of all the local processes in which this temporal parameter is used. Now, to conclude with this presentation, I have shown how temporal service level agreements are a crucial element in the definition of business collaborations. And there is a conflict between the need for business secrecy of the local processes composing the inter-organizational process and the need to set temporal SLAs because these will need to access the events internal to local processes. This is mitigated by the exchange of temporal variables as parameters. We have shown that an approach based on temporal constraint networks would allow for a temporal reasoning which is effective and guarantees the confidentiality in conjunction with the use of temporal variables in the definition of business collaborations. As future work, we are planning to carry out a systematic investigation of the application patterns which the use of temporal variables as parameters enables in business collaborations. And we are working on the design and the implementation of procedures which would support the negotiation of parameter restrictions in cross-organizational collaborations. Now, this is it from my side. I would like to thank you very much for your attention, and I think I will be very happy to answer your questions when it will be the time during CAiSE Forum.